So in class, we saw LeNet. This is maybe about 1995, created by Jan LeCunha's team. It was created for very low resolution black and white object recognition. And in particular, they were focused on this handwritten digit task. Now, the rest of today's lecture will basically be a trip down memory lane. We're going to start with LeNet, which is basically, I would say, the first useful convolutional neural net, and then talk about all the milestones that eventually get us to the state of the art in object recognition through time. Let's fast forward from 1995 to maybe the early 2000s, say 2001. So the dot-com bubble just burst, but machine learners are still in the heyday of kernel methods that we've all heard so much about. The nice thing about kernel methods is that they usually lead to nice sort of convex optimization problems, and this means that you have nice computational algorithms. You can prove theorems about them. You can show that these algorithms converge quickly, and then you can also study the statistical properties of the resulting estimators, the resulting predictive models, and you have all these tools to show that the resulting predictive models are going to do very well. Things like VC dimension that we've seen before, yada, yada, yada. And so life was really good. The problem was that these methods are just not doing so well on certain classes of problems, in particular problems with unstructured data. So images, audio, text, or more generally natural language processing. They're just not doing that well. And the idea basically is that with hindsight now, at that time it was very difficult to sort of see, but with hindsight, what was wrong is basically if you think about a kernel method, when you start at the very beginning, you have to choose your kernel, right? You have to choose this feature map, and therefore this feature map also comes with the kernel that computes inner products in the feature space associated with that feature map. Therefore, you have to choose this feature map, you have to choose this kernel at the very beginning. And this choice is made in a data independent manner, right? Maybe you go to logistic regression, you want to fit a kernel logistic regression, you just, before you even begin, you pick a kernel, say I want to fit quadratics or I want to fit cubics, then I pick this polynomial kernel of the correct degree, and then I kernelize the problem, and then I sort of turn the crank and out pops this kernelized logistic regression model. But the key is here that this choice of polynomial or maybe a radial basis kernel, this is usually made not in a data-dependent way. Sure, you might try a couple of examples, but you don't really sort of fit the kernel to the data. Okay, there were efforts to sort of learn kernels from data, but these sort of also didn't really get anywhere. And so this is the state of the world at the beginning of the 2000s. You had all these methods with beautiful theory, beautiful computational and statistical theory, but they weren't doing very well. And with hindsight, the reason they weren't doing very well is because the features that they were using, these are essentially linear methods on top of features, and these features were not learned from the data. The linear model on top of these features, right, the coefficients, these are learned on the data. That's what the kernel method, and when you fit the kernel method, what you solve for, what you optimize for. But the features themselves, right, they are not touched. And this, with hindsight, is the problem. I mentioned that in computer vision land, kernel methods were not working so well. And so what they were doing is they were doing something similar, but they were not using kernel methods. It turns out that there are many feature maps for which you can write down the kernel, but this kernel function is not so easy to compute. And so this means that if you try to kernelize this problem, there's no real computational gain from using the kernel trick, because evaluating the kernel is difficult. And so what they did then is they simply, instead of relying on kernel methods, they just decided to do the feature engineering themselves. What actually happened in computer vision, most of the effort in computer vision research was devoted to this feature engineering challenge. If I give you a task, some object recognition or scene recognition, image segmentation, you would spend most of your effort designing good features for this specific task. Now, once you sort of manage to come up with a good set of features, everything worked fine. So You could put an SVM or your simple logistic regression on top of these very carefully designed features, and the methods would work. They would have decent performance, not great compared to today's standards, but they were passable performance. The only issue is that this need to do feature engineering severely limited how fast the field can progress, because every time you have a new problem, you have to sit down and try to construct these new features, and this was done completely manually, and so and this is more of like a art than a science, and so it was a very slow and agonizing process to come up with these features. Some people call this the seedy underbelly of computer vision at the time, and so this need to do this feature engineering was really limiting computer vision. So, that was the 2000s. So you guys are probably just born or not even born yet. I was in high school, middle school. But now let's forward to 2010. Okay. So by then, hopefully, most of you guys have come into existence. I just graduated from undergrad, and what happened this year was this dataset ImageNet came out. Okay, and this was a very, very large dataset at the time. Today, it's still considered not a small dataset. It's like, I would say it's moderately sized. Okay, it's kind of like the first dataset that you would run, let's say, real data experiments on. Like the smallest dataset that if you ran experiments on, people would be like, this is considered like a real experiment, not just some simulation. These days, if you run experiments on MNIST, people look very suspicious at you. They'll just assume that you couldn't get your method to work on any bigger dataset like ImageNet. But anyways, this was a very large dataset at the time. So by comparison to, let's say, MNIST, instead of 60,000 images, right, you have over 1 million images. Instead of 10 classes, you have over 1,000 classes. Instead of images that are just 30 by 30, you had images that were at least whose resolution could be measured close to using megapixels. And finally, the images were color instead of just grayscale as before. So this was a monumental leap in the size of data sets that were available at the time. And ImageNet was put together for a variety of things, but one of the things that it was used for is a object recognition competition that was run annually. Okay, and there are a couple instances of the competition that sort of went by without too much happening. I mean, people would use this old school sort of computer vision approach, right, where they did this very careful feature engineering, and they would get reasonable results, but nothing, no breakthroughs occurred. So a couple iterations of this image recognition competition has gone by, and we come to 2012. And in this case, the Toronto group, so AlexNet is named after Alex Krzywinski. He's from this machine learning group at Toronto, headed by Jeff Hinton. And they submit an entry that just completely blows every other entry out of the water. Okay, and their entry is notable because they did this completely different approach. Okay, they used this neural net. We'll look at the architecture in a little bit, and it actually looks a lot like LeNet, just a bigger version. But the fact that they sort of completely blew away the competition made people pay a lot of attention. Okay, and just to understand the context, remember, computer vision at this time, right, as I said earlier, they were doing this very careful sort of hand-tuned feature engineering, and then usually slapping some type of linear method like an SVM on top of these features. And the issue, right, with our hindsight again, is that when you did this feature engineering, right, you're still sort of manually coming up with features, right? And so these features are probably, they're better than if you just randomly chose features, but they're still far from optimal. Okay, and AlexNet, being a neural net, it not only learned, right, this last layer classifier, which is you can think of as the last layer in a multi-layer perceptron, but it also learned the features. Okay, and this, in hindsight, is what really sort of turned the page. Right, we went from hand-engineered features to now automatically learned features. And so AlexNet won this competition in a very dominating fashion, and they did this in a completely different approach. And this is what made people really pay attention. Look at the architecture of AlexNet. AlexNet deals with much larger images and images in color, right, compared to LeNet. And so you start with this 3, which is the 3 color channels, RGB, and 224 by 224 images, and compared to just grayscale 32 by 32 images for LeNet. Okay. And then you have this typical convolution plus pooling strategy. And what's notable here is that you have much larger kernels, much larger strides, right, and a vastly larger number of output channels, so 96 instead of 6 here. Okay. The pooling channel switched from average pooling to max pooling now. Moving from the first couple layers to the network to the middle of the network, you see that here it's actually very similar to LeNet. It's much deeper, right? You have many more convolutional layers sort of stuck in the middle, and this really increases the expressivity of the network. Gives you a lot more nonlinearity to exploit, makes the network much more flexible. And this is in some sense needed because remember, here you're trying to recognize 1,000 classes instead of just 10 classes. Now we move to the very top of the network. So of course, AlexNet has to recognize 1,000 classes. So the final output is a dense 1,000 dimensional vector compared to 10 for LeNet because that one only has to recognize 10 classes. But even before, right, the size of the hidden layers of this multi-layer perceptron at the very end, they have been increased from orders of tens or hundreds to 4,096. Okay. And the idea here is that again, if you wanted to recognize 1,000 classes, then you probably need to have more than 1,000 dimensions to sort of capture necessary information to distinguish between 1,000 classes. At this point, you might say, hey, AlexNet and LeNet, they don't really look that different, right? You've always have this, initial number of convolutions followed by pooling. Yes, average pooling became max pooling. And in the middle, you have a lot more convolutional layers than LeNet, but still, broadly speaking, the structure is the same. And then at the end, you have this multi-layer perceptron to convert all these extracted features to finally your 1,000 posterior probabilities. Okay, so the structure and LeNet still seem pretty similar. So what gives? Well, there are a lot more tricks that went into training AlexNet. So if you think back to a lot of tricks that we mentioned earlier, dropout, right, using ReLU instead of TANH or sigmoid activations, data augmentation. This is all these tricks that I showed you. These were first used in AlexNet. And they were not so much that it was sort of boosting the performance of AlexNet, but it was that it was necessary to use these tricks because AlexNet at this point had gotten much deeper, much larger. And so if you didn't have a lot of these tricks, you would actually not be able to train. And so, for example, changing the sigmoid activation function to ReLU, right? AlexNet is a much deeper network than LeNet. And so the gradient vanishing problem is, if you remember, the vanishing problem gets worse, right? The deeper the network goes, the more number of layers you have, right? And so for AlexNet, which is a much deeper network, this gradient vanishing was a much bigger problem than for LeNet. And so switching to ReLU, right, at least from sigmoid, at least, guaranteed that you always have gradient signal at least for a half space, right, for each neuron. You added dropout to essentially regularize the internal layers, right? Not just the beginning, not just adding input noise to regularize just the input layer of the network, but also the internal layers you're regularizing with dropout. And then another important thing is data augmentation. Let's say you have this picture of a cat, you would, let's say, zoom into various patches. You would maybe distort this by, darkening it, lightening it, changing color. But this type of data augmentation, you can think about it as dropout for the input layer. This is also very important. And all these sort of tricks that had to be, developed in order to successfully train AlexNet. All right, so if you look at AlexNet, it's just really a much bigger network than LeNet. And so it's roughly got, 1 order of magnitude more parameters. Right? It's got 2 orders of magnitude. It's 2 orders of magnitude more computationally intensive to evaluate. And this is really a reflection of the times at that time. Memory is, and actually today, memory is still in some sense the bottleneck, the limiting factor. AlexNet was actually trained on 2 GPUs. It had to be sort of split between 2 GPUs, and a lot of the work, a lot of engineering that went into training AlexNet, aside from all the tricks that I just talked about, was just writing low-level code to sort of synchronize the training between the 2 GPUs. Right, that time you didn't have NVLink, and so this for AlexNet it was really just a lot of very small things sort of coming together. Nothing sort of individually, made a huge difference, but they sort of all came together. If you compared, the architecture to Linux, it was not that revolutionary. I mean, it was just bigger and more sophisticated in every way. But these pieces all came together and to basically really, this is really like a paradigm shifting moment in machine learning. I would say that for you guys who remember the introduction of ChatGPT, right, this sort of totally changed machine learning. AlexNet was a bit like that. Before then, there was this paradigm where people are always using, kernels or hand engineered features with, methods that, were very sort of computationally elegant, statistically elegant. You could prove theorems about them. And then afterwards, everybody sort of immediately dropped this paradigm and all switched to beating deep nets. So of course, AlexNet was a computer vision, but soon after, people took these ideas and went into speech, went to text, natural language, and so all the unstructured data modalities. But it all really started with AlexNet. Okay, so that was AlexNet. Now, this was, remember I said AlexNet came out of Toronto. So across the pond at Oxford, these folks from the Visual Geometry Group, VGG, they sort of saw AlexNet and they were like, oh, looks like AlexNet just took Linux, made it bigger, made it better, and now they just demolished this competition. Maybe if we go even further, make the network even bigger, even deeper, that we'll do even better. And so this is the idea behind VGG. Okay. Unlike AlexNet and LeNet, which are just single architectures, VGG actually is a entire group of architectures. Okay, and the idea is that at this point, the network has gotten sort of so big that essentially they're sort of constructed not sort of by sort of choosing individual layers, like what happened in AlexNet and LeNet, but basically sort of stacking identical blocks of layers. And so a lot of the engineering that went into sort of designing each individual block. But once you design the block, what you do is you just stack them. And so you'll hear networks like VGG19. That just means that it's the VGG block, but stacked 19 times before the final multi-layer perceptron output layers. And so this is the first time that you see this type of blocking. Or we still see it today, right? For example, you go to your transformer architecture, they'll be like, oh, this block, this self-attention block stacked, 45 times or whatever. That's the same idea here. So about the blocks. So one thing that they found when they were designing these blocks is that actually, and this is a pattern that's sort of repeated in deep learning a lot, is that actually if you have more layers, but each layer is simple, and you compare this to having fewer layers, but each layer is more flexible, more expressive, usually more simple layers wins. So a deeper network with simple layers at each, with simple operations at each layer, compared to a shallower network with a very complicated operation at each layer. Usually the deeper networks with simpler layers will actually overall turn out to be more expressive. And so when they designed the VGG block, they actually use very simple layers, so 3x3 convolutions, and but they stacked them up quite deep. And so this created the VGG block, which was then repeated to construct this family of VGG networks. This is a overall graphical depiction of the VGG architecture. Like I said, VGG is actually a whole family of methods, right? And they all consist of these VGG blocks, which are the same across all of these networks, just stacked a different number of times. So VGG 16 is stacked 16 times, VGG 19 is stacked 19 times, so on and so forth. Okay. So this is VGG, and compared to AlexNet, you see that it's just a much deeper, bigger version of AlexNet. But the high-level architecture is still kind of very similar. You have these, convolutional split pooling layers, and at the end you have this multi-layer perceptron. Let's go back to this idea. Remember this VGG, right? The people that are working on this visual geometry group at Oxford, they were just saying they were just thinking that they can take AlexNet and just AlexNet was a scaled up version of LeNet, so they just make a scaled up version of AlexNet, and this should even do even better, right? And this was true to an extent, okay? So on an absolute level, they were able to improve the accuracy over AlexNet, okay? However, they did this at drastically increased memory footprint and drastically lower throughput, okay? And so on the x-axis, what you see here is that, so this is a plot of, a lot of the common convolutional net models. And what you see is the AlexNet, right, is all the way at the bottom right. So the number of, its throughput is very high because it's a relatively small network, but its accuracy was, not very high. So high throughput means it's, all the way to the right side, but accuracy not very high means it's, on the lower end, right? So it's on the bottom right. VGG sort of increases the memory footprint. I should say, the size of the dot represents the memory footprint of each of the models, okay? So the VGG family of models, remember this is multiple of these models, they had much bigger memory footprints, right? So their dots are much bigger, and they're to the left of AlexNet. So their throughput, the number of samples they can process per second, is much lower, okay? But they are more accurate, okay? But they are more accurate. However, if you look at this plot, the VGG models, they have the biggest dot, right? They have the largest memory footprint. And what you notice is that all these other networks, there is a bunch of models that are sort of above VGG, right? And the dots are small. That means that they sort of got comparable performance. They got better accuracy, but with smaller memory footprint. And so VGG in some sense was the end of the line for this idea of just taking LeNet and scaling it up. You took LeNet, scaled up, you got AlexNet. You take AlexNet, you keep scaling up, you get VGG. But this is in some sense the end of the line. After this, it starts becoming impractical, and people had to look for new ideas in order to get further improvements. How do we reduce the number of parameters? The idea here is to really focus on these last layers, because it turns out that despite you look at this network, AlexNet or VGG, right? There are only 3 multi-layer perceptron layers at the end, but they actually account for a vastly outsized portion of the memory footprint. These multi-layer perceptron layers, they have a lot of parameters, especially compared to the convolutional layers, which essentially you're just looking at this very small filter. Those are the parameters, and compared to the pooling layers, which have no parameters, right? And so despite the fact that there are only 3 layers at the end, they actually make up a very large very large proportion of the memory footprint of the model. And so the next innovation that we're going to look at is basically how you reduce this memory footprint for these very last layers, how you replace the multi-layer perceptron with something else. And this brings us to what's called a network-in-network layer, or a NIN layer. So to really understand the NIN layer, how it works, you have to understand the idea of a one-by-one convolution, okay? So what is a one-by-one convolution, right? Remember, convolutions, you're supposed to sort of be convolving with this, filter, right? So you're sort of pulling information across neighboring pixels within the same channel. What does a one-by-one convolution do? It doesn't, have any type of, pixel, doesn't aggregate information from your neighbors. What is it doing? Well, if you think about what this one-by-one convolution is doing, it's really aggregating information, right, across channels, right? You can think about it as you have all these channels, right? Then you fix a pixel across all the channels. Okay, let's say the top left pixels, right? Now you look at, let's say you have, like 512 channels or whatever. You look at the set of all top left pixels. Now you have a vector of length 512, right? And now you can imagine applying a multi-layer perceptron to this vector, right? This will allow you to share information across these channels. Now, this is not as general as a full multi-layer perceptron, right? Because you are restricted to only sharing information across the same pixel across all these channels. You cannot share information across different pixels from different channels, right? You can share information across channels, but it has to be between the same pixels. And so this is how this one-by-one convolution gets around this problem of, or how one-by-one convolutions enables passing information across channels. Now, passing information within a channel, that convolutions can do. So what you need to do is you need to stack these one-by-one convolutions with regular convolutions, right? And this will allow you to, freely share information across all the pixels. Right? Of course, you might have to do, this a couple of times, right? You might have to stack a couple of these layers instead of, just doing one massive multi-layer perceptron layer. But even if you stack a couple of these layers, it turns out that you still have a net savings in parameter count. And this is what really enables you to save on parameters without detracting too much from the expressivity of the multi-layer perceptron layers. So as I said earlier, you're going to combine these one-by-one convolutions that pass information across channels, but only within the same pixel, with regular convolutions, which do not pass information across channels, but they share information within channels with neighboring pixels. When you put these two together, now you have the ability to share information between pixels across all channels, right? Even different pixels. And so this is a NIN block where you sort of combine these convolutions with these one-by-one convolutions. And this essentially takes the place of a full sort of multi-layer perceptron layer, okay, at the cost of greatly reduced memory, at the benefit of greatly reduced memory footprint. Like I said, these NIN layers were essentially used as drop-in replacements for the last few multi-layer perceptron layers at the tip of LeNet, AlexNet, VGG. Now, when they first did this, this actually didn't perform too well. So it didn't do as well as VGG. But this was a step in the right direction. And as you see, other architectural changes, when combined with these NIN layers, will allow you to truly improve upon VGG. We'll see that in a bit. For the next big breakthrough, this will come in the form of what's called the GoogleNet. Okay, it's made by Google. It's a play on the word LeNet. They add Goog and GoogleNet. Now, the problem that they're faced with was a very real problem. Let's look at what has been done before, right? So, for example, we had LeNet, right, which used a bunch of maybe smaller convolutions. And then we went to AlexNet, right, which used a bunch of bigger convolutions, right? The kernel size was bigger now. And then you went to VGG, and now there was just a lot more variety of convolutions. Yes, they were smaller, but there are also, more of them, deeper, each VGG block. And then you had NIN networks, which were just regular convolution, and you tack on a bunch of one-by-ones to facilitate information sharing across channels. Okay. And so these are all, various architectures. Which one do you choose, right? In some sense, you can think about a convolution as sort of locking in a sense of scale, right, for that layer. And so, for different objects, maybe some are bigger, some are smaller, you may not want to lock in, a scale of that layer. And so the question is, which one do you choose, right? Sure, you can maybe try and, tailor, the size to a particular problem, but then this sort of detracts from the generalizability. And so they wanted it all. Okay, they wanted to be able to, in some sense, select the best layer, the best kernel size. The idea they came up with. Okay, instead of having to choose one, why not have it all? Okay, and so what this is doing is this is a block, right? Remember, we're sort of constructing these networks with blocks. So I'm looking at a block. So there's an input to this block, and I'm going to pass this input through basically multiple possible paths, okay? So the first path, let's say I just take a one-by-one convolution, right? The next path, I take a one-by-one followed by a three-by-three convolution, and then I take another one-by-one followed by a five-by-five convolution, right? And then maybe I just take a pooling layer followed by a one-by-one convolution. These are 4 different paths. Now, instead of having to choose among them, what I do is I just take the outputs of all of these individual paths, okay, and I just stack them, right? I concatenate them. Now, of course, I have to sort of, choose these paths, carefully so that the outputs are all, compatibly sized, right? So that I can actually do this concatenation at the very end. This essentially allows you to, find sort of the best way, to sort of it preserves information all the scales. Now, this is just the same view again, but of the same insertion block, but with the channel sizes specified. Insertion blocks as just drop-in replacements for a convolutional layer, just like sort of nins with convolutions were drop-ins for dense multi-layer perceptron layers. Insertion blocks are now you can think of as improved versions of convolutional layers. If you count up the parameters very carefully, they usually have less parameters, and during the forward pass, they take less compute. And so this sort of you can think of this reduction in number of parameters as some type of capacity control, and so this leads to good generalization. And the fact that inside this block, they're not fixed on convolutions of a particular size, right? Also, sort of compensates for the flexibility loss by reducing the number of parameters, and so they ensure good generalization by keeping the number of parameters small, but they also try to keep the function class flexible and expressive at the same time. Okay, so this is what the overall GoogleNet looks like. Okay, so at the very beginning, you still have these standard convolutional stages with pooling, and this is basically to build in some type of translation invariance into the network. So the initial layers, you always have these convolutional layers to make sure that just because you jiggle the inputs by within the within the convolutions, you don't change the output by too much. So stage 1 and 2 are sort of these initial layers. This is by and large fairly similar to AlexNet and LeNet. And then afterwards, this is when you start having these inception blocks. Okay, in between here they use 3x3 max pooling, but the inception blocks are sort of really just sort of what's doing the work. And so these inception blocks, notice they're repeated, right? So in stage 3, the inception block is repeated twice. In stage 4, the block is repeated 5 times. Stage 5, the inception block is again repeated twice, and so on and so forth. The stages maybe a bit more closely. So here again, right, stage 1 and 2, very similar to AlexNet. You're just looking at sequence of convolutions with poolings, right? Here, maybe the only distinctive thing is that they've added this 1x1 convolutional layer in the middle. But other than that, it's very similar to AlexNet. At this point, maybe some of you guys are a bit confused about the various dimensionalities that's going on inside the inception block. So let me just step through this very, very carefully and very, very thoroughly. So at the beginning of the inception block, right, you have 28 by 28 images, 192 channels, right? So each channel is a 28 by 28 image, and you have 192 of these images stacked up in some sense. So let's look at the far left path, right? So in the far left path, you apply a 1x1 convolution, and so again here you're sort of just sharing information across pixels, across the same pixel over the 192 different channels, right? And so when you do this, what you have, you end up with a 28 by 28 image, but now with only 64 channels, right? That's what the 1x1 convolution does. So that's the left path. That's very easy. Let's look at what the second from the left path does, okay? So now you still apply a 1x1 convolution, right? But here, instead of 64 output channels, you have 96 output channels. So what you end up with 28 by 28 by 96. Okay, so 28 images, 96 of them. Okay, and then you apply a 3x3 convolution with 128 filters, right? And so what this ends up with, right, is now you have 28 by 28, right, with 28 by 28 with 128 images now, right? I mean, the idea is you take this 28 by 28 96 images. That's the output of the 1x1 convolutional layer in this second path, right? And then to each of these images, right, you're going to apply a 3x3 convolution, right? So and then you're going to get with obviously with the appropriate padding and stride so that it stays 28 by 28, and then for each of these convolutions, right, you take all these 96 images that come out, and you're going to average them. You get one image, right? And you repeat this 128 times, right? So this is how you get 128 images. Okay. Now, okay, so the next two are pretty easy once you understand the first two. So the first one, the third path, again, you take your 28 by 28 images, you apply a 1x1 convolution, except now there's only 16 of them. Okay, so you get a 16 28 by 28 images. You apply 5x5 convolution, now with 32 filters, right? So what you get is, again, 5 by 5 with the appropriate, padding and a stride, so that you always stay within, 28 by 28 images. And so now you get 32 28 by 28 images, right? Again, what's going on is you take this 5 by 5 filter, right? You apply it to each of the 16 images that's coming out of the 1 by 1 convolutional layer, right? And then you average these. To get a single image, right? And you do this 32 times, right? And this is how you get, a 28 by 28 images, 32 of them, right? And the last layer, again, this is very straightforward. You just have a max pooling before a 1 by 1 convolutional layer, so you're going to get out essentially 28 by 28 images, but 32 of them, okay? And so now what you see is that you take 64, you add 128, and then you add 32, and you add 32, right? So remember, the leftmost path comes out 64 28 by 28 images. The second path comes out 128 28 by 28 images, right? The third path comes out with 32 28 by 28 images, and the last path comes out also with 32 28 by 28 images, right? They're all 28 by 28, but just different number of channels. So you add up the total number of channels, you get 256. That's what concatenation means. So at the end, you end up with 256 images of 28 by 28. Right? That's what this inception block is doing. Progress, through Google and Net. So you eventually, through these inception blocks, you're going to steadily increase the number of channels in the output, but you're going to decrease the size of each image, right? So here you see instead of 256 28 by 20 images, now you have 480 14 by 14 images, right? Like when you go through these this inception block, you're still sort of reducing the dimension of the image, because fundamentally convolution and pooling, they reduce the dimension of images, right? But because you've sort of gone through many convolutions, many rounds of pooling, each of these pixels are sort of in some sense very informative. They're not so much pixels anymore, but you think about this features, right? So here you have 480 features. That's maybe a better way to think about it. And so then the feature size goes to 512 channels and eventually to 132 channels before you and then 1024 channels before finally you apply this global average pooling operation, and out comes your 1024 final feature layer, which you then pass to your last dense layer to get to the desired number of classes. Details about this inception blocks. So they actually went through many different versions of them, and so they slowly sort of updated it to keep up with the times. Of the kind of changes that they made. So on the far right, you see this is the old inception block that I sort of showed you. On the left, what you see is that what they did was they looked at this third path, right, where you had 1 by 1 convolution and then a 5 by 5 convolution, and they replaced this with a 1 by 1 followed by a 3 by 3 followed by a 3 by 3. Right? They made these sort of small tweaks, and again, this sort of goes along the line of you want to make simpler make each layer simpler. So a 3 by 3 layer, has fewer parameters than a 5 by 5 layer, right? You want make each layer simpler, but you want to stack more of them to compensate for, to make the overall pipeline more expressive. And this is what they're doing here. Here's another example of some of the changes that they made. So here they took the 1 by 1 and then 3 by 3 convolution path, right? This path, they replaced it with a 1 by 1 convolution and a 1 by 7 convolution and a 7 by 1 convolution, right? So the idea here is that you want this type of asymmetric convolution to, the 1 by 7, this is a very sort of flat kernel, so you're aggregating information across the width of the image, right? And a 7 by 1 convolution is very tall kernel, you're aggregating information across the height of the image, right? And so obviously you need both. And so that's why you have 1 by 7 followed by 7 by 1. And then it did something similar again to the third path where you used to have the 5 by 5 convolution. Here they have, 2 stacks of this 1 by 7 and 7 by 1 alternating convolutions. So when you use these inception blocks, this is when you finally improve upon VGG. Remember, VGG were these large pink dots right in the middle of the screen, and so inception or GoogleNet is the V3. This is above, and so the accuracy is better, right? Throughput is the same, and notice the memory footprint is smaller because the size of the dot is smaller. Okay, so here we're sort of approaching the state of the art. Remember at the very beginning there was this 1 by 1 convolution. So there are 1 by 1 convolutions throughout the inception layer. So the NIN network idea sort of found its way into sort of parts of the inception block and parts of stage 1 and 2. And so here we're sort of we're seeing all the ideas sort of come together, and we're getting pretty close to state of the art. in order to get to, so you see on this plot, the state of the art, those are the purple dots, right? And the last idea that we need to get those purple dots are the idea of residual connections. So that's what we're going to see next. So finally, we get to resonance or residual networks and residual connections. So this is another one of these ideas where the original motivation was something quite different, but it just happened to work really well. And then afterwards, people started looking into it and then discovered the real reason for why they work so well. So the original idea behind resonance was, again, to avoid this gradient vanishing problem. Okay, you see why it was developed in a little bit. Or how the particular architecture sort of avoids this gradient vanishing problem. But the modern explanation for why resonance works so well is that it ensures a nested function class as you progress up in depth. Okay, so let me unpack that statement. Let's say you have a network that's L layers deep. Okay, with whatever modules you're using in each layer. Okay, whatever blocks you're using, VGG, Inception, whatever. Now you're interested in adding another layer on. Let's say you want to go from L to L plus 1 layer. Let's say go from 10 to 11 layers. Okay. Now this 11 layer network, right, intuitively, right, is more expressive. Right, it's now got more parameters, right? It's deeper, right? It is a more flexible function class, right? But it's actually not so obvious, right? It's actually not so obvious how this function class actually is more expressive. So for example, if you took the 11 layer network, right, and you attempted to use it to replicate the function that the 10 layer network was representing before, right? Well, how would you do this? Well, what you would do is you would, let's say, copy the weights, right, of the first 10 layers over into the first 10 layer. You copy the weights of the 10 layer network over into the first 10 layers of the 11 layer network, right? And then you would want to set the last layer to somehow just essentially not to touch anything, right? The last layer should basically be the identity function, right? Okay. Wow, this is possible for a lot of network architectures. You really have to think pretty hard about how exactly are you going to encode an identity function in a multi-layer perceptron layer, in a convolutional layer, right? If there's pooling involved, right? How exactly are you going to encode the identity function, right? It's not so obvious how you're going to do this. And so when you build these networks and you build them to be much deeper, it's oftentimes not clear that you're actually meaningfully augmenting the function class. You're meaningfully making this network more expressive, because in order to sort of express, right, simpler networks, or networks that have less depth, like shallower networks, using your deep network, you actually have to set the parameters of this very last layer kind of carefully. And let's say that you're inside a learning problem, and you actually have the 10 layer networks is enough, okay? And you've just in some sense over parameterized the problem. So you're going to use a 11 layer network to learn what a 10 layer network could really already is sufficient. So then what you need to do is you need to, ideally what happens is you spend the first 10 layers learning what the 10 layers network would have learned, and then for the last layer you learn the identity function. But the problem is that learning this identity function, remember, you have to set the parameters of this last layer very carefully in order for it to be the identity, in order for it to be the identity function, right? And so this identity function still needs to be learned, right? And it may not be so easy to learn this function, right? Depending on what the layers are. Now, if there was a way where you could reparameterize the network so that the identity function for each layer is very simple to learn, right? That will automatically guarantee this nested function class, that your function class is growing, right? And that will also make sure that if you ever ran into this problem of overparameterization, right, you wouldn't have, the network could very easily sort of take care of it. It could very easily replicate the output of a 10 layer network with 11 layers, right? And so ResNets is the trick that does this. ResNet do, right? Let's before we talk about resonance, let's recall like a normal network. Okay, so the normal network, let's say you have these blocks, right? And so let's say in these blocks, let's say you have some you pass it through a bunch of weights. So this is a linear operation or an affine operation, and you pass through an activation function, and then let's say you pass through another layer of weights again. Okay, let's say this is your block. Okay, now in order to learn a identity function for this block, right? It's actually not so trivial, right? Because depending on where your activation function is, right, you might need the weights to end up at the outputs of the weight layer to end up at a very particular spot, right? And so it's not so easy to learn an identity function, okay? The idea behind ResNets is instead of having these layers update their inputs directly, right? What you do is you always carry a copy of the input, okay? And then what the layer does is it adds to this copy of your input, okay? So instead of looking at the input x to f of x, okay, you're now looking at the input from x to x plus f of x, okay? So you always carry around this copy of the input and you're always adding to it, okay? Now, this architecture is very easy to learn the identity function, right? You just take this set of weights, you set them all to 0. Then this f of x will value to 0. And because you are carrying this copy of the input around, right? If f of x is always outputting 0, then you're effectively learning the identity function, right? This makes it very easy to learn the identity function. And this is the key idea behind ResNets. At the ResNet block in greater detail. Here's the actual ResNet block. It's not weight plus activation plus weight. So the actual ResNet block is you first take a 3x3 convolution, you pass through a batch run, okay, and then you pass it to the ReLU activation layer, and then you do 3x3, and then you do batch run again, okay. And this is the f of x part, okay. This is the change, okay. And you take the input to this block that I just described, and you keep it around, and what you do is you take the output of this block and you add it to the input. Okay, again, if you just set the 3x3 convolution layer to 0, right, then this block is going to learn the identity function because it's going to learn a 0 function, and therefore, when you add it to the input, the net effect is the identity function. Okay. Now, remember I said that ResNets, this is in some sense a backward justification to it, right? They developed this method to solve the gradient, vanishing and exploding problem, and then they found out later, right, that it worked really well, and the reason was this type of nested function class explanation. And so since at the time they were not trying to go for nested function class, they tried out a couple other weird ideas. For example, instead of just taking the input and carrying it around, you actually apply a 1x1 convolution to the input, which is not bad. It's still almost the identity. And so yeah, there are actually many flavors of ResNet blocks, and we'll see some more in the next slide. The other sort of source of variation among ResNet blocks is where do you exactly bring back the input to this block, right? Do you bring it back before the batch run layer at the end? Do you bring it back after the batch run layer? The other way is, where exactly do you sort of, stick the batch run layer, right? Do you how more generally, how do you order this convolution, batch norm, and ReLU layers, right? Do you go conv first, then batch norm, then ReLU, maybe ReLU, then convolution, then batch norm, or batch norm, then ReLU, then convolution? All three permutations, right? So basically, people tried all of them, and there doesn't seem to be one that works the best, and so. There is a standard ResNet, but it's not like these other things were noticeably worse. I think the standard ResNet is just the original ResNet paper, just because none of these work better. They just sort of went with the original. But there are all kinds of variations on the standard ResNet block. One thing about the ResNet block is that because at the end, right, instead of just modifying the input, you're going to sort of add, right, that you're learning to change the input, so you're going to add whatever f of x is back into the input. This imposes the condition that f of x must have the same dimensions as the input, right? And this is not a problem, and we saw how to do this, by adjusting the padding and the stride, in the inception block. But you do have to be sort of very careful when you're designing these ResNet blocks, because they do have to output things that have the same dimension as the input. Okay, so what happens inside ResNet? Well, you take these ResNet blocks and you sort of stack them up, right? So the simplest, ResNet 18 has 18 of these blocks stacked up. You go up all the way up to, I think there's a ResNet 50, there's a ResNet 150 even, and they're exactly what it sounds like. ResNet 50 is 50 of these blocks stacked up. ResNet 150 is 150 of these blocks stacked up. Okay, so this brings us to about the state of the art for object detection, or just generally image tasks. If you, let's say today, you want to do some type of, machine learning task on images, what I would probably recommend you do is you go to, you download ResNet 50, let's say, or the biggest one that you can fit on your GPU, and then you maybe delete the last couple layers, maybe delete the global average pooling layer, and then use the output of this ResNet stack, right, as feature extractor, and then just train, let's say, a standard linear method on top of these features, or maybe a multi-layer perceptron with one hidden layer on top of these features. And that's what I would probably recommend you do. This really brings us to the state of the art, and these ResNets, remember there are these purple dots on the plot that we've been showing you. ResNet, see there, in some sense they're at the very top, right, in terms of accuracy, but their memory footprint, the size of these dots is still quite small. So that brings us to the state of the art. I should say, if you look at this plot, right, there's this, you can think of it, there's like a frontier, right, which is sort of this, if I sort of look at the convex hull of this, this downward sloping curve, this frontier towards the, basically, if I try to sort of wrap a piece of string around all these dots, right, and I look at the upper right sort of corner of the shape that's formed, this is in some sense the Pareto frontier of this model zoo, right, that we've looked at thus far. Within this convex set, right, so for example, if I look at maybe if I look at AlexNet and maybe the ResNet, maybe in between one of the VGG models sort of lies on a line segment between the dot of AlexNet and the dot of the ResNet. So what this is really saying is that you can actually realize the performance of this VGG model by just taking an input and then randomly shuffling it to ResNet or randomly shuffling it to AlexNet. What the proportions are depend on where this dot falls in the line segment between AlexNet and ResNet, right? If it falls very much towards ResNet, then I will pass the point to ResNet more often than passing it to AlexNet. But the idea is any sort of model in the interior of this set is now in some sense useless because you can recreate its performance with models on the frontier.